Hello, in this video today what we're going to be talking about is how do we solve trig equations that have been transformed graphically. That's going to be the main point of everything that we're doing today. Okay, so there's going to be two sort of sections to this video. I'll put it in the same thing. But essentially the first section is going to be focused on actually drawing the trig function correctly, right, based off of a transformation. Okay, you can see this trig function here with sketching the graph of the function y equals 2 sine x on the diagram below. So firstly, we're going to have to draw that. And then the second section of the video we're going to be talking about is answering this question down here, right? Using the graph that we have drawn up above to solve this equation, 2 sine x minus 1 equals 0 for the domain of 0 to 2 pi, okay? So that's the two sections that we're going to break it down into. And here is where we're going to start looking at actually how to graph our function, okay? So if you're at this point in the Mathematics Advanced course, I would expect you to be able to graph the original sine, cos, tan, and all of the reciprocal functions without much issue, okay? So we're going to use the original functions to understand what is actually happening when we transform sine of x to 2 sine of x, okay? So I drew this quite quickly earlier, all right? Here is our function that we have here of y equals sine x. We call this one of the original trig functions, and you'll notice here it has a peak at pi on 2, x-intercepts at 0, pi, and 2 pi, and it has a trough, we often call this, at 3 pi on 2, right? But you can just think of them as maximum and minimum. The other thing that I've added onto this graph here is this red line from the center of our trig function up to the peak. It's the same distance from the center to the peak as what it is from the center to the bottom of the trough of the wave. Okay, I just haven't drawn a particularly great graph here. This is just to illustrate what's going on. We call this thing the amplitude. Okay, now the thing that affects the amplitude is the number that's out the front of the original function. Okay, right? So the way that we look at it is whatever number out the front here grows or shrinks our amplitude away from the center of our trig function. Okay, so you'll notice on our original function, the number here out the front of the sine x is just 1, and that is what correlates here with our maximum y value that we have on the original function. Okay, so if we were to put a 2 out in front of this trig function, what would end up happening is that it would stretch the graph away from the x-axis to have a peak here occurring at 2. Okay. In the same vein, what's going to happen is it'll stretch the trough away to, instead of occurring at -1, it would stretch all the way down to occur here at -2. Okay, we call this a vertical dilation, right? And it's a transformation just by stretching your graph in the vertical direction. Your intercepts will not change when you do this. So it'll look like the exact same intercepts, but your graph is just stretched away from the x-axis. So let's have a look at how we draw this. One of the important things to notice when we look at this particular question is, what's the scale of our diagram appearing on here? We don't have too much of an issue with the vertical scale. That's going up in 1, 2, 3, and 4, and we've already established from our graph before that our peak is going to occur somewhere here at 2 and somewhere down here at -2. Okay, so we understand that's how our function is going to work. However, you'll notice something slightly different in terms of the number scale that this graph is going up in along the x-axis. This can cause us a little bit of an issue. Why? Because you'll notice that our scale that we're going up in here is by pi on 2 for each step. That's slightly different to this one, which is going up by pi on 3 at each particular step. So what you need to do before you start drawing your graph is you need to adjust it so you have pi on 2 and 3 pi on 2 on your diagram. Okay? This is not too hard, right? You just count the number of squares that you have until pi, and then you go halfway between it. Okay? So this will give me pi on 2 going halfway between 0 and pi, and then I'm going to do the exact same thing from pi to 2 pi, okay, which will give me 3 pi on 2. Now that I have that understanding, okay, what I can do is I can start to actually transform my graph. So you'll notice this here has an amplitude, okay, equal to 2. So that just means it stretches away from the graph, and the maximum will occur at 2, and the minimum will occur at -2. Nothing else changes in regards to that. So the intercepts will stay the same. Remember, the intercepts occur at 0, pi, and 2 pi. So let's put the intercepts in at 0, pi, and 2 pi. Okay, and the only thing that changes is instead of our peak occurring here at 1, it now occurs here at 2, above the pi on 2. That's why we've changed our scale to be able to draw this. In the same vein, our minimum, our trough, will occur down here at 3 pi on 2. And then all this is just a simple matter of connecting the dots to draw your graph. Okay, so let's do it. Okay, you want your graph to be as accurate as possible, but while still being a sketch. Remember, you're not here to win an art competition, but you do want to convey the information as accurately as possible to the reader. Okay, so here we are. We've just drawn our graph. That is y equals 2 sine x. It's always important that we label it. Okay, that would be enough for us to end up receiving the 2 full marks for this particular question, right? Understanding that we've changed the scale and we've got the correct amplitude along with the shape of the graph. Okay, so that's the first part of our question. If we look carefully at the next part, it says use the graph to solve the equation 2 sine x minus 1 equals 0 for 0 to 2 pi. Okay, that's then followed by ensure that you clearly identify any construction used to arrive at the solution. Okay, there's 2 important parts to this question that students can often miss. The first one is this part, using the graph, and the second part is identifying any construction. What many students will actually do is they will look at this particular trig equation and they will go along and they will solve it algebraically. Okay, that's a problem. Not because of your mathematical ability, but because what you're actually being assessed on in this question is using the graph that you've drawn above in part I to solve this question. So you will actually lose marks if you're not answering the question correctly. Okay? All right? The other thing is identifying any construction that you use to arrive at the solution. Okay? So we'll talk about this in just a moment in terms of the construction. Construction is just extra lines that you add in that you want to talk about as you sort of go through it. Okay? So first things first, I want to start off with our equation that we have here. 2 sine x minus 1 equals 0, right? So this is now our second part of our video that I want to talk about. You'll notice up here, our original function that we're given is 2 sine x. So I am trying in my head to think about how can I manipulate this equation to have 2 sine x equals something. All right, and that's just by moving the 1 to the other side. Okay, so I end up with 2 sine x is equal to positive 1 after I've sort of solved this, just using your basic equation stuff. What that means is, where does my function, okay, equal, oh, sorry, my apologies, the values of y equals 1. We're essentially solving simultaneous equations here, right? So all I do is I just take my y value of 1 and I plot a line across it. This is some of the construction line that we were talking about before, okay? Now, I want to clearly identify the construction line that I've done, so I'm just going to label this as a value y equals 1. All right? You can see now there are 2 solutions that you can expect, okay? Here and here. All right? Now, our next part that we want to do is we want to try and identify the x values that we can use to solve this equation. So we need to look from the points of this intercept, and this is why it's important to have an accurate sketch, right? To see where the x values occur below on the x-axis, okay? So all I've done is I've just drawn 2 vertical lines down to my x-axis to give me 2 points, all right? Now, if your graph's accurate, you'll notice that you travel a certain distance from 0 to halfway between 0 and pi on 3. Now, that's going to give you your initial solution that you have here. So if you're traveling halfway from 0 to pi on 3, well, that's just half the distance to pi on 3. So our first solution using the graph, which is what we're trying to do, is equal to half of pi on 3, pi on 6. Okay? Now, there's a couple of different ways that you can think about this. This next solution that you have here that we're talking about. I would find it easier to think about this, going backwards from pi towards the halfway point between 2 pi and pi on 3. Now, the reason why I do that is I like to use the symmetry of trigonometric curves, okay? So if this is going to be pi on 6 distance away from 0, it's also going to be, and I'll draw this up here in red, pi minus pi on 6 distance backwards, using the whole symmetry of that curve. That would be the easiest way that I would suggest that you sort of go about it. Now, that means for your second solution, if you simplify this, that's just going to give you 5 pi on 6, okay? So your second solution that you have occurring in the range of 0 to 2 pi is 5 pi on 6. So that is how you use your graph from a previous question to graphically solve this particular equation here, okay? Right? So to recap everything that we've done, okay, if you look at my blue curve, what we've done is we've taken our original trigonometric function of sine x and transformed it with a vertical dilation, right, to change the amplitude to be maximum values of 2 and negative 2, maximum minimum values of 2 and negative 2. And then we looked at how we can use the graph from the previous question to solve the equation 2 sine x minus 1 equals 0. Now, just remember, you can solve this algebraically. No one's saying that you can't. But because in this question they're specifically asking you to use the graph, this is the technique as to how you would approach it. Okay? Understanding how to use the scale of the graph and just being careful and accurate with your sketch as you go through. Okay? I hope this has helped you out. All right? And yeah, I hope you've also learned something new. Thank you very much.